Hi students, now the topic is equilibrium constant from the Nernst equation. For example, we take one reaction, these reactants are converted to the products. So these are stoichiometric coefficients A, small a, capital A plus small b, capital B gives rise to the C, C, D, D. So we are going to write for this reaction, next equation is E cell equal to E naught cell minus RT NF ln concentration of products by concentration of reactants, products by reactants. So we take the concentration C power C, D power D, and A power A, B power B. So these are stoichiometric coefficients. Also we are going to write like this way for some chemical reaction. Okay. So in Daniell cell, we observe in Daniell cell zinc plus Cu plus zinc solid plus Cu plus 2 equilibrium, Zn plus 2 aqueous plus Cu solid is. This is a actual reaction. So we take the equilibrium constant for this reaction. So in Daniell cell, during the cell reaction, the concentration of zinc increases and concentration of copper plus 2 decreases. Concentration of Zn plus 2 increases and concentration of Cu plus 2 decreases. How? We observe in this in galvanic cell. So Zn plus 2 ions, Zn plus 2 ion concentration is increases because of Zn is going to liberated in the formation of Zn plus 2. So number of ions Zn plus 2 ions are increases in this, and in this Cu plus 2 is converted to the Cu. So it is going to deposit on the surface area of this electrode. Okay, Cu plus 2 ions are going to deposited at this electrode as Cu solid formation. So what is mean of that? The Cu plus 2 ion concentration is going to decreases and Zn plus 2 ion concentration is going to increases in this cell. Okay, so during the chemical reaction, and we get that how much amount of the current is produced, electricity is produced by the using of voltmeter. Okay, so this is the actually principle. So during this reaction, this type of concentration changes is take place, and it's after some time. So we observe after some times we shall note that there is no changing in the concentration of Cu plus 2 and Zn plus 2. Okay, after some time we shall note that there is no change in concentration of Cu plus 2, concentration of Cu plus 2 and Zn plus 2. Okay, so at the same time the voltmeter gives 0 reading. So what is mean of that? The changing concentration between the anode and cathode is attain equilibrium. That means the concentration changes is 0, no concentration changes. So what is mean of that? The both ions are going to take place at equilibrium condition. Okay, at equilibrium condition. So we are initiated like this equilibrium. So ions, anodic ion, cathodic ion going to take place equilibrium condition. So at that position the voltmeter gives 0 reading. So we take the E potential, E cell equal to 0, EMF equal to 0, E cell equal to 0, E cell. So we are going to write the next equation, E cell equal to E naught cell minus 2.303 RT by NF log Zn plus 2 concentration by C plus 2 concentration. Actually this is the next equation. So we take the equilibrium constant for the next equation. So now we are going to write the equilibrium constant for the next equation. So in this we observe E cell equal to E naught cell minus RT by NF ln Zn plus 2 by Cu plus 2. So this is the actually next equation. So in that you observe E naught cell equal to 0, 0, E naught, E cell equal to 0, E naught cell minus, so we removal of ln, we take the 2.303 RT by NF log Zn plus 2 concentration by Cu plus 2 concentration. Okay, so both concentrations are going to take place equal. That means there is no change in concentration of anode and cathodes at that time at equilibrium condition. So these concentrations of the both one is same. So we introduce the one of the constant, that is equilibrium constant Kc. So you take this in this position, E naught cell equal to 2.303 RT by NF log Kc. Okay. So also you rearrange this by the substitute the values of R value 8.314, okay, and T is 298 Kelvin temperature, and F Faraday 96487 coulombs like, okay. So you introduce this E naught cell equal to 0. 0.059 by 0.059 by n equal to how many number of electrons are exchanged between the cation and I mean exchanged between the electrode cathode and anode and cathode. So 2 electrons, so we take 2, okay. So 0.059 by 2 log Kc. So this is a so E naught cell equal to, so in this place the this value E naught cell E cell equal to 0. So you take the directly E naught cell equal to 2.303 by RT 2.303 RT by NF log Kc. Okay. So also you take the Kc equal to E naught cell by log Kc equal to 0.059 by 2. Also rearrange this log Kc equal to 0.059 by 2 into E naught cell. So this is a equilibrium constant formula, okay, for the next equation, okay. And next one is electrochemical cell. Electrochemical cell and Gibbs energy of the reaction. Electrochemical cell and Gibbs energy of the reaction. So when a cell reaction is take place, energy is produced with decreasing the Gibbs free energy of reaction. In thermodynamic point of view, we introduced that is Gibbs free energy. So this Gibbs free energy is going to decreases for the spontaneous chemical reactions. So in this spontaneous chemical reaction, when the cell reaction take place, the energy is produced. Which energy? Electrical energy. So with the decreasing Gibbs free energy of the reaction, so decreasing in Gibbs free energy equal to, so chemical energy is converted to electrical energy. Electrical energy means that is a current. So in spontaneous chemical reactions, decreasing of free energy equal to quantity of current produced, okay. So if 1 mole of electrons it produces, that is equal to the 1 Faraday electricity. So 1 mole of electrons are produced during the chemical reactions, for example. So it is equal to the 1 Faraday of electricity. If n mole of electrons are produces, that is equal to the n Faraday electricity, okay. Do you understand about this? Chemical energy is converted to electrical energy in electrochemical cells. In spontaneous chemical reactions, okay. In spontaneous chemical reaction, delta G value is going to delta G Gibbs free energy is going to decreases, okay. So that is equal to the how much amount of electricity is produced. So that is decreasing free energy equal to quantity of current produced. Okay. So finally we take electric work done equal to NFE cell. Okay, final electric work done equal to NFE cell. N is N equal to number of Faradays and E cell is voltage potential. Okay, potential. So work equal to NFE cell. So in this work taken as a decreasing free energy, so we take the, in the place of W we take the delta G equal to decreasing free energy, we introduce minus, that is the reason, minus NFE cell. Okay, for the spontaneous chemical reactions in thermodynamic point of, I mean the spontaneous process, which are the spontaneous process, those delta G value is negative. So in this delta G equal to minus negative minus NFE cell. NFE cell. Okay, at standard conditions, this is the delta G equal to NFE cell. N is a number of electrons. Okay, number of electrons. F is a Faraday. E is a potential energy. Okay, so we calculate by using of these values. We calculate the delta G of any one of the chemical reactions in electrochemical cell. At standard conditions, delta G not equal to, we take the delta G as taken as delta G naught equal to minus NF E naught cell for the standard conditions. So you take that E naught cell as per the next equation for equilibrium constant. E naught cell equal to 2.303 RT by NF log Kc. This is a next equation for the equilibrium constant one. Okay, so we introduce this delta G equal not equal to minus NF E naught cell equal to which one, 2.303 RT by NF log Kc. So NF both one cancel, so we get delta G naught equal to 2.303 RT by no RT, so direct no by, so delta G naught equal to 2.303 RT log Kc or ln, you directly you take delta G naught equal to removal of 2.303, we get in the place of log we get ln RT ln Kc. Okay, delta G naught equal to RT ln Kc. Okay, so this is a another one, and also this is also another one. Okay, by using of this delta G we calculate the sum of the Gibbs energies, some of this for example in standard electrode potential of the Daniell cell is standard electrode potential E naught cell equal to, question is given, E naught cell equal to 1.1 volts, 1.1 volts. Okay, 1.1 volts. Calculate the standard Gibbs energy for the reaction. So reaction is a Zn plus Cu plus 2 gives rise to the Zn plus 2 plus Cu. This is the question. Okay, so E naught cell value is given. So what is the Gibbs free energy? So delta G naught equal to minus NF E naught cell. This is the formula. Okay, so as per this formula, so you introduce that n, how many number, n means what is the n, what is the value of the n? N is a number of electrons, present, I mean number of electrons are exchanged between the anode and cathode. Okay, so in this Zn is converted to Zn plus 2, Cu plus 2 is converted to Cu. How many electrons? 2 electrons. You take n equal to in this 2 electrons. Okay, F is a Faraday 96487 coulombs, and E naught cell is E naught cell equal to 1.1 volts. Okay, substitute these values, delta G naught equal to minus 2 into 1.1 volts into 96487. Okay, coulomb mole inverse. So we get minus 2 1 227 in joule mole inverse. Okay, also you convert kilojoules also. Okay, so this is the way of solving problems. So you have some in-text questions. In-text question, calculate the remaining in-text questions, its g values and some inert cell values. Okay, so next one is after this next one is next of the next after that next topic is electrolytic solution. Okay, electrolytic solution. Electrolytic solutions in this substance which produces ions in solutions and conduct electricity or electrolytes. Okay, what are the which of the substance are going to produce ions in solution and they are allowed to pass the current, those are called as electrolytes. So we take the some example in this NaCl, sodium chloride, HCl, hydrogen chloride, and CSCOH, acetic acid. So these are all act as electrolytes. So these are going to ionized. So that means these are going to form ions in solution and they are allowed to pass the current. Okay, so that means the and conduct the electricity. So these are called as electrolytes. So NaCl, Na plus Cl minus, CSCOH, CH3CO minus H plus, KCl, K plus Cl minus, like that. Okay, these are allowed to pass currents. So those are called as electrolytic solutions. And non-electrolytic solutions. So these non-electrolytic solutions are do not produce ions in solution and cannot allow to pass the electricity. So those are called as non electrolytes. Example, carbon tetrachloride, benzene. Okay, these are non-polar solvents. These are not allowed to flow the current. Okay, so these are called as non-electrolytes. Also, you take the some of the starch solutions. Okay, so these are belongs to the non-electrolyte solution. And these electrolytic solutions classified into two types as strong electrolytes and weak electrolytes. Strong electrolyte means the complete ionization is take place. So which of the substances are going to ionize completely? Those compounds, substances are called as strong electrolytes. Okay. So in definition, completely ionized substance in solutions are called as strong electrolytes. Example, NaCl, HCl, KCl, KOH, H2SO4. So these are strong electrolytes. So also you take the strong acids HCl, H2SO4. These are also going to ionize completely in solution. Okay. So complete ionization is take place. So these are strong electrolytes and weak electrolytes. And strong electrolyte means they are allowed to pass the they are allowed to pass the current completely because of complete ionization is there. And weak electrolytes, partial ionization is take place in some substances. So those are called as weak electrolytes. So they are going to allow to pass the current, but compared to strong electrolytes, weak electrolytes very less. Okay. For example, if we take the acetic acid is going to form acetate ion and H plus. So these are going to form ion formation is take place, but also it is a reaction is take place backward direction also. That is the reason we initiated equilibrium in this. Okay, so this is a weak acid, so also it is taken as weak electrolyte. Okay, so this is a type of electrolytes. And after that, next we take the some words, some definitions for this electrolytic solutions. Okay, resistance, we take the first one is resistance. It is oppose the flow of current. It is oppose the flow of current, that is called as resistance. Okay, and it is measured with by using of Wheaton bridge, and you already study in the physics, in your physics. Okay, and R is directly proportional to the length and inversely proportional to the A. L is a length, A is a cross sectional area. Okay, L is a length, A is a cross sectional area, and directly we take the R proportional to the L and inversely proportional to the A. R proportional to the L and inversely proportional to the A, and directly we take R proportional to the L by A, and R by removal of this proportionality we introduce the this is rho. R equal to rho into L by A. R is a rho, also called as resistivity or specific resistance. Okay, so this is a resistance. So rho R is a resistance. R is directly proportional to the length. So this is a length between the two electrodes. This length or L value. So if the L value is increases, resistance is going to increases. If the L value decreases, so the resistance is going to decreases. That means conductance is increases. Okay, so you observe in this cell, and also you observe in this cell length. This is a between the two electrodes. This is taken as length. So if the length is increases, resistance is increases. If the length is decreases, resistance is increases. And A is cross sectional area. So what is meant by cross sectional area? So this electrode area, this area. So in this area, so that means the electrode area is contacted with this electrolyte. So this area is a cross sectional area. So if the cross sectional area is increases, resistivity is decreases in this also. So more contacted. So if the more contacted with electrolyte in of the electrode, so that is a cross sectional area. If the cross sectional area is increases, resistivity is decreases. That means conductance is resistance is, if the cross sectional area is increases, resistance is decreases. That means conductance is increases. Okay, so this is the cross sectional area. So this is resistance, and we have units. Units are ohm. We initiated the symbol ohm or OHM, ohm, and this symbol is for the units of resistance. And also you take the SI units, kg meter square by s cube and a square. Okay, so this is the resistance. After that, next we take the resistivity. Resistivity is a rho, cell having 1 meter length and 1 meter square area, that is the resistivity. So we introduce the formula rho equal to R into A by L. Also you rearrange this resistance equal to R equal to rho into L by A. So you take the rho place, rho equal to R into A by L. Okay, so this is a, you take rho into R equal to L into A. Okay, so also you take the rho equal to L into R into A. So you after the next rho equal to R into A by L. So rho equal to ohm. R is the units of the resistance is ohm, and cross sectional area A is a meter square. L is the length meter. So this is a, after removal of this we get the meter. So rho units are ohm, meter. Okay. So this is a resistivity rho. Resistivity is indicated with rho. Okay, and next one is conductance. Conductance, inversion of inversion proportion of resistivity is inverse proportion of resistance is conductance. Flow of current through a substance is, the substance is like metal is there, electrolyte is there. So through a flow of current through a substance. If it is metal, that is metal conductor. If it is electrolyte, that is a electrolytic conductor. Okay, so in this you observe the conductance means flow of current through a substance. Substance is like metal or electrolyte is called conductance. Okay, conductance. Those substances are called as conductors. As metal, metal conductor; as electrolyte, electrolyte conductor. Okay, so we introduce the conductance with G. Conductance is introduced with G. G is a inversely proportional to the resistance. Okay, G is inversely proportional to the resistance. So in the place of R, we already know R equal to rho into L by A. So G R equal to rho into L by A. So G proportional to the 1 by G inversely proportional to the 1 by R plus L into A, rho into L by A. So G proportional to the, so you rearrange this one. So G proportional to the A by rho into L, and removal of proportionality, we get the G equal to K into A by L. So K is a kappa, okay, not kappa, kappa. So G equal to K into A by L. This is a conductance formula. Okay. So units are in this ohm inverse, Siemens or mho. Ohm inverse, inversion of ohm. Ohm is a resistance conductance. Inversion of ohm is a mho. Okay. So this is a units of conductance, and where K is, in this K is a conductivity or specific conductance. R is a resistance and rho is a specific resistance. G is a conductance. K is a specific conductance. Okay. So, K is also called as kappa. Now we are going to discuss conductivity or specific conductance. So, in this conductance cell having 1 ml electrolyte solution, 1 meter length and 1 meter square area of cross section. So that is a have the conductivity. So K equal to 1 by rho. So K is a conductivity. Conductivity is that means rho is a resistivity. Inversion of resistivity. Inversion of resistivity is conductance. Okay. So inversion of resistivity is conductivity. Inversion of resistivity is conductivity. So K equal to 1 by, in the place of rho equal to R into A by L. So you take the K equal to 1 by R A by L. So by the